power quality today, and I'm going to cover the topic in a number of ways. You know, what's our experience at Rockwell Automation? What's it really costing our customers? How can we prove it? And then finally, what you can do about it. I do have a demo that we'll be sharing with you today, and we've got, for those online, we'll get a camera going so you can actually see me doing the demo. And also, if you're online, you can write in questions, and we can stop. So again, I don't want to go too fast for anybody. If you have a question that's not making clear sense to you, don't hesitate to stop me and just ask about it. All right, there we go. So let me just start by very quickly saying we've been doing this a long time. So I've got a slide up here with testimonials, a lot of big Fortune 500 companies on it. The company list of companies using our product to solve power quality problems is very, very long. Many thousands of customers today all over the world. And these people are typically willing to talk about it and their experience and why they're using it. So again, don't be afraid to ask. We can always get a reference. There is literature that Rockwell's put together on various applications for various industries, whether it's food and beverage, automotive, semiconductor, healthcare, just about you name it. Again, lots of experience in lots of different markets all across North America. The product that we're going to talk about today, or the solution I should say, we call it a DISC, and it stands for Dynamic Sag Corrector. And this product or solution comes in sizes all the way from 2 amps in size to 2,400 amps, so and kind of everything in between. So it really is designed to solve the power quality problems you might be having, you know, at a control panel level, on a machine level, on a bus level, or the whole plant. And we've got examples again and customers with all these types of solutions out there. And I'll explain to how these things work and why you might use them as opposed to anything else. One of the things that I think is most critical to understand when we talk about this problem and what it might be costing us is how to measure that cost. And folks, when it comes to power quality, that cost is measured in unscheduled downtime. We can all point to cases where we have equipment broken, power supplies blow up, drives fail, et cetera, et cetera, et cetera. But at the end of the day, the real money is in the unscheduled downtime. And so when I'm going to just briefly show a couple slides here on this, but the point is simply this. It might not be just the amount of time that people are standing around twiddling their thumbs while they're waiting for the line to come back up. It might not be just the scrap material that you've created, right? It could in fact be an opportunity cost. And let me give you an example of that. In the automotive business, we service pretty much all the industry, all the players in that industry, and a couple of big ones here in North America. Of course, General Motors would be one. Another one closer to home maybe is BMW. Now, in the BMW world, they pretty much sell every vehicle they make. So when they talk about what's their downtime, unscheduled downtime cost, they really talk about it as an opportunity cost. If they're down for an hour, that's 70 vehicles that they will never make. At $70,000 each, that's more than $4 million of downtime costs that BMW suffers. At General Motors, they tend to think about it in terms of how many minutes people are standing around, right? And in their world, the reality is if they're down for an hour during the week, they can make it up on a weekend, or maybe they don't have to because they've still got cars on the lot. So it's a different perspective, and as a result, they approach the problem different ways. BMW solves that problem at the highest level, at the bus level, 1,600 amp bus level solutions. General Motors solves their problems at the mini disc or the single phase level, protecting control panels for paint shops and paint lines and so on. So the results can vary even in the same industry based on that cost of unscheduled downtime. At the end of the day, what we want to help you do is to be able to produce a return on investment picture that looks like this, where we've got some investment here in the blue down here that you might have to solve the problem, but you immediately start paying that back, and over a short period of time, that just compounds. And honestly, if you can show a picture like this, it's pretty easy to get the CFO to sign off on doing something about it, right? So that would be the goal. But that's not where we start out. We start out in a very different place. And so I'm gonna take you through that a little bit. And if you bear with me, this is my picture of your manufacturing facility. All right, so it's pretty simple as it would have to be. We've got power coming through the plant wall. It comes inside and it gets distributed amongst various pieces of automation. We try to balance our phase A, B, and C on the control side. And out there on the automation side, you know, we've got controllers, we've got maybe robots, processors, contacts and sensors and counters, whatever it might be, encoders, depends on your business, right? But imagine this, pretty much the same for everybody. What happens when one of those machines, or one of those lines go down? Well, in my picture, it's the guy with the hair on fire, right? That's what happens. So somebody, when that happens, is responsible to get that equipment up and running again. And again, with every business, the story is going to be different. You know, if you're a blow molding plastic and the blow molders go down, that plastic hardens in a very short period of time, and then the job is going to be stripping it out, cutting the pipes, who knows. Could be hours before you get going. In another case, it might be as simple as you walk up to a machine and push the button. Now, everybody's got their sort of worst case scenario that's very application specific, but we all have the best case scenario. It's the same. Push a button and it goes. So let's just talk about pushing the button and it goes. Imagine the machine goes down, a guy gets out there, hair on fire, pushes the button and it goes. Okay, not so bad. What happens a week later when that same machine goes down? Hey, he pushed the button last time, he's probably going to push the button again, right? It worked last time. Well, what about 2 weeks later when it happens again? Or the following week on the fourth try? I mean, really what happens is these guys are conscientious people. They're looking at machine A that's down for the fourth time. Machine B right next to it's been running the whole time. It hasn't gone down. They're supposed to be the same. What the heck is going on? At some point, our skilled trades guys are going to say, hey, something's wrong. We're going to fix it. So they take the machine down. They spend some time troubleshooting it. They come back with a solution. Maybe they take off a PLC, you know, send it back to Rockwell. Put on a new one. Everything goes. They get the unit back from Rockwell. What's it say? No problem found. Right? Anybody ever heard that one? No problem found. Today, that is the answer on 70% of all the warranty returns. Right? And it's just not a Rockwell issue. It's an industry issue. So what really is going on across North America is that we got people doing their best they can, troubleshooting the equipment the best they can, and then fixing what isn't broken, right? And it's happening all the time. It's a $2 billion a year problem, folks. It's significant. So what if this was going on outdoors at that same time? What would our guy do? He'd look out the window and see lightning and go, I know what it is. I don't know exactly what it is, but it's got something to do with power. He pushes a button and away it goes, right? But if he doesn't drive by, you know, the accident that happened up the road, where the guy hit the pole or got hung up on the wires, or he didn't happen to see, you know, the things that do happen out there. Once in a while we blow up a transformer and something happens and things break. Or, you know, if you're in Florida, you don't happen to see the Cuban tree frog climbing the poles, you might not realize you've got a power quality problem going on, right? Now, just a little background, this Cuban tree frog I'm talking about. The Lakeland Power Company sent me this picture. Before I came down to do a talk for them, they said, Brian, you got to understand, the #1 power quality problem we have in Lakeland is tree frogs. And I've been going to Florida a long time since I was a little kid, and I imagine I've seen tree frogs. They're about 1.5 inches big, and they make a heck of a lot of noise. He said, no, you don't understand. We have a new species. They call it a Cuban tree frog. It's got all the little suction cups that can go right up the poles just like before, but it gets to be the size of a bullfrog, so a foot long instead. So these guys are up there chasing bugs, up on the wires, you know, up on the poles, and they jump or stretch out, and they get between two places they shouldn't, and they cause a short. And all of a sudden, they've just created a power quality problem. And guess what? All the manufacturing lines around there, they got to see it. They got to feel it. And in some cases, if it was close enough, they went down, right, as a result. Now, why does that happen? Well, it's because of the way the grid's designed. Think of it as a machine that's really designed to work without any interaction, just automatically. And before we get Tourette's, I'll stop this. So the power comes out of the power plants. It moves its way down through our transmission system, through our sub-distribution, all the way down to the neighborhood levels, right? Depending on how big a plant or facility you are, you might pull off at higher levels on the grid. But anywhere we short the grid, it's a short on the grid. So that short could be caused by our tree frog. It could be caused by a lightning strike, right? It's a short to the grid. And if they don't do anything about it, if we can't get the short off the line, what's going to happen? The grid's going to collapse, right? And in fact, we all experienced that in 2003, right, on the East Coast. We had a transmission level failure. Actually, it was a line that went to ground. They didn't realize what it was quickly enough. Pretty soon, every power plant on the East Coast pumped everything they were making right into the ground. The grid was collapsing, and they were in danger, frankly, of blowing the plants up. So they shut it all down. Took about a week for us to recover from that one. But that doesn't happen all the time, thank goodness, right? And the reason is there's a breaker out there on the line. That breaker is called a recloser. And that recloser is designed to open when it sees the short nearby. But since most of the time it's lightning, it closes again because it's already gone, right? And they don't want to have you out of power. So if the short is still there, now it's going to stay closed just a bit, because honestly, if it's the branch or on the line or our tree frog or the squirrel, what do they want to do? Well, we're going to fry it. We're going to have a little frog legs today, and we're going to open that line up so the frog can drop down where we can get him. And then we'll close the line a third time, and at that third try, if the short's still on the line, that breaker's going to pop open and stay open. Now, typically, these three events happen in about 2 seconds of time. There is some adjustment to it, and it can be set to 4 or 5 tries. And in some parts of the country where we're a long ways from service, they do that, right? Because if at all possible, we want to clear the problem without sending trucks. But once it's an outage, now they're going to send the trucks, right? So the grid will heal itself typically within 2 seconds. Now, if you've experienced this at home and you got lost power, you'll see the 2 flashes and then the power goes out. That's what's going on there, is this recloser is trying to clear the event. Right? Well, here's what it feels like. At the point, now imagine I've taken the grid, which really looks like a bowl of spaghetti if you drew a map of it, right? And I pulled it all straight so I could make sense out of it. And there's about 50 miles of wire between substations. So that's what we're looking at here. And wherever that short is, whether it was our squirrel or the lightning strike, whatever it was, it's a dead short to ground at that point on the grid. And the grid starts to collapse, meaning all the electrons start to flow to the short. Then our breaker pops, and everything snaps back up and is good for a moment. Then let's say it closes again, the short's still there, all the electrons are rushing to that short, right? So the fact is that the closer you are to the epicenter of the event, on the wire now, physically, how close are you connected to that point, will determine how deeply your voltage is going to sag during the moment in time that short's on the line. That's what makes it so difficult to troubleshoot these things, because every time it happens to you, it feels different. The last time a squirrel was 2 miles away, and the time before that, the guy hit the pole 20 miles away, and tomorrow it might be next door, right? And every one of those events are going to affect you differently, depending on how low that voltage goes. There's another aspect to this, and it's the one that causes damage out there, and it's the one we often deal with when we see shorter life on our drives or our power supplies are destroyed, and sometimes it actually looks like we got hit by lightning. The front end of the power supply, the diode rectifier circuit, right, is burned right up, right? And people will say, oh, we must got hit by lightning. No, lightning might have hit, but it hit down the road, and what you experienced came at the end of the voltage sag that the lightning caused, and this is why. So imagine I flip the switch on in this circuit, and I start to charge the capacitors. Now, managing that current flow into this diode rectifier circuit is something called a soft charge circuit, and it just manages a current flow. When we get about 80% fully charged on our power supply, drive, whatever it is, we close a bypass around the soft charge circuit so that we have access to current when our drive or our power supply is doing its job. There's nothing to slow it down, it's doing its thing. Along comes our squirrel. We end up with a voltage sag, and all the electrons that were over there on our capacitor, they just took off and went to ground. So immediately the power supply needs to be charged up. It needs energy, it's hungry, right? So at the very end of the voltage sag, a current inrush takes place to charge those caps back up to where they should be. But since nobody ever shut it off, the bypass still exists around the soft charge circuit. So the current inrush that happens at the back end of the voltage sag has nothing to manage it. And the inrush currents that you're going to see are between 5 and 17 times the inrush current that you get at startup. Right? Now this is going to be, in some cases, the power supplies are just going to blow. Right? In other cases, it's going to shorten their life. You imagine what happens when that current hits? I heat up. Right? I've just hit it with 17 times the current that was expected, so the diodes get hot. And then they cool off. Now when they get hot, of course, they expand. Right? Then they cool off. It's a plastic package. They get hot and they cool off. So the number of times you hit it over the life, you're expanding and contracting these diodes until finally it mechanically fails. So that's why we see drives last a lot longer. They're a really rugged power supply than we see some other power supplies. Once is enough, and those things will go the first time. This is a picture of what that looks like. This is normal inrush current on the left. We see the peak is right at the beginning, as you would expect at startup, and then the current's being well managed to a steady state. Same circuit here, we have a voltage sag, and you can see where the sag ends, and just at the end of the sag, we had to change the scale here, the peak inrush current on this thing hit 50 amps. So, and this is the most conservative view of this problem. So it is, you know, you will see damage, you will see shorter life on components. The more often you're having a power quality problem in your facility, hitting your facility, the more it's going to affect your components and your gear. And finally, the last piece that I like to share with people, because sometimes power quality seems quite mysterious. At the end of the day, it all is traceable to some physical cause. There really is something. I mean, it could be as simple as a loose wire in the outlet, right? It's chattering back and forth or on the machine. Now you've got a power quality problem going on. In the grid world, 60% of the time it comes from weather, like the branch falling on the tree, the lightning storm that hits. The other 40% of the time, it's the cause by, I'll call them stupid animal tricks and stupid human tricks. Right? The moose gets on the wire. How did he do that and why? I don't know. But I don't know why this guy got up on the pole and blew fire either. So he was from California. At least I know that much. But but reality is, you know, we hit the poles and knock them down. We have accidents, and squirrels and animals get in the way, and birds, quite often it's a bird problem. And that ends up hurting us. So what do we do about it? So the very first thing that we need to do is to understand it. And to do that, we've got to do some monitoring. Now, there's another aspect. Who's the guy who needs to understand it most, meaning most urgently? He's the guy with his hair on fire, right? So here's the guy who's running out to the machine. If we could just tell him that this is a power quality event, he's not going to fix something that isn't broken. He's going to get it running again, whatever that means, right? And he's going to chalk it up to, okay, one more downtime event, took me 15 minutes, caused by power quality. So you're going to start to create this smoking gun. I had a power quality event, I had some downtime. What's it cost me? Now to do that, with Rockwell, we offer a couple of different solutions. One is called a Power Monitor 5000. That product is capable of monitoring your current as well as your voltage. And it can do event capture monitor. It lives on a Rockwell backbone, a factory talk network, and it can display that information on man-machine interfaces throughout the plant. The other way to do that is with a product that we make called an Isense monitor. Now that Isense monitor is a voltage only monitor. Doesn't monitor current at all, but it's an event capture voltage monitor. And so when an event comes in, and you can see a capture right here at the top of the screen, the little red dot is when the event started, and this is when the event ended. And the Isense will capture 3 cycles before the event started, the event, however long it lasted, and then 3 cycles after the event ended. And it's going to package that data, and it pushes it to our server, and the server turns around and immediately sends to the owner of the monitor a report that tells them what just happened. And that report can go by way of an email message, so if you have a smartphone, you get it all, or a text message. So even if you don't have a smartphone, you get a message within a minute of the event, you're still running to the machine, you're still looking to figure out what's going on, and now you know. You just had phase 2 drop to 40%, and that's why you went down. So getting that data is critical. Now, the Isense gives us another advantage, and that is the fact that it's networked with other Isense monitors, and that's what Isense looks like. It's a device about 12 inches wide, I think it's 11 inches, and 12 inches tall, about 3 inches deep. You got power comes in on one side, 3-phase power on one side, and an Ethernet cable or a phone line goes out the other side. That's how it communicates. Now it communicates back to the cloud, to our server, and when we see an event coming from a monitor, we immediately look to see if we see that same event on any other monitors. And if we do, then automatically we send another report to the owner of the monitor that corroborates this as a grid event. You know that you didn't create it in your plant because we saw it on the grid coming at everybody, right? So you get a corroboration report. The other thing, of course, is because it's in this environment, there's no limit to the number of people that can get that report, not only the instant report, but go back and pull out a whole year's worth of data. And of course, the key guy, there's no limit to the number of users, and every user can actually have their own adjustment. So the plant manager probably doesn't want to know about every transient that hits the plant, because there's a lot of them, right? They don't really affect you much. But when the voltage drops below 60%, you probably went down. Maybe that's the time to send him a message. So everybody has their own adjustment. Skilled trades guys are going to be set a little higher so they can see those transients perhaps. For the plant manager, you'd probably set it a little lower so you don't get bothered by stuff that doesn't take your plant down. If we look at this map, this is kind of a push-pin map of zip codes where we have one or more of these monitors, and a couple things to know about it. First of all, the monitors exist in factories primarily, right? Every General Motors, I mentioned them, auto plant in North America has had an Isense monitor on it for the last 12 or more years. And in fact, all around the world they're monitoring. It also might exist in power company substations. So we work with a lot of power companies that actually will put the monitor in a substation on PTs and share the data with that user who's getting hurt, right, by it, because now they can have a real conversation about what really happened instead of everybody guessing. They're also in hospitals. So GE Healthcare for the last almost 15 years now has been putting our monitors in all over the world, and particularly in North America, in hospitals where the power comes in and affects their MRIs and CTs and other equipment, so they get a handle on what's hitting them. When you look at the map, you can see it's heavily weighted where we have industry, and there's just not too many out in Wyoming, right? It's just no sense monitoring the cows always. But this is an example of the kind of data you get from a couple of monitors that sometimes surprises people. So here on, in this case, the monitors are about 20 miles apart from each other. In one case, we see a sub-distribution level with an event that took place on June 29th. It dropped to 71% remaining voltage at that site. While at the same time, 20 miles away, at another site being fed at a distribution level, so when I say sub-distribution, I'm talking neighborhood level, 12.8, 13.2. At a distribution site, we're looking at maybe 47 kVA, 69, you know, it could be as high as 139 like some of the auto plants, but you're up here high on the grid. This guy got hit at the same event, but he dropped to 61% remaining. Everybody know why? He was closer, right? Simple as that. He thought he would be protected from all these events, and in fact, He sees fewer, but when they come close, they hit you, no matter what level of the grid you're being fed at. Our GM plants, why do they monitor these? On average, they go down 4 times a year because of power quality. They don't lose power. Niagara Falls doesn't quit going, right? Unless they shut the plant down, they have power, but still 4 times a year, they go down even when they're being fed at 139 kVA. So you just never know. Where's that squirrel going to show up next? So let's get a little closer to home. This one is some data that I pulled from Watson, Louisiana, and it shows, and I'm going to show a couple of these, but these are reports, and I've got, for those of you that are here, let me press one around to each side, and you can take a look at these, pass them on. These are a couple other reports, and they all are formatted the same way. So on the top of the screen, what we see is a couple of big pie charts. The one on the right tells me, in this case, out of 24 events that they saw, 23 of those were less than 2 seconds in duration, 96%. Again, what we'd expect to see. The numbers today show that 98% of all the events on the power grid are less than 2 seconds in duration. So it's not surprising. On the left-hand side, what we're seeing is the magnitude of the event, meaning how bad was it. The ones in yellow, so in this case more than half of these events, were not likely to have caused downtime. They happened, but we rode through them. The equipment had enough ability to do that. The other half of the events are kind of split into 2 groups, the largest of which are the ones that drop between 60 and 80% remaining. These, by nature, are very difficult to figure out. Machine A goes down, but not machine B. Why is this happening? You very seldom will blame it on power, and you're going to very often blame it on something else and chase your tail. The ones that drop below 60% in the red, well, those are typically going to get the power label because everything just went down, and they're really scrambling to figure it out. On the same screen here, what we see is a couple other important ones. The magnitude duration chart in the lower right-hand corner. It really is a picture of how low did it go and how long did it last. And we're looking at the worst case for each of the events. So every one of these little diamonds, and for those of you that are looking at the other reports, that event had at least one phase that dropped to 60% remaining and lasted maybe 150 milliseconds. I don't know by looking at this if it had 3 phases do that, but I assume the worst case, right? So this is plotted assuming that worst case. The other thing that I see here is a couple of lines that work their way through our graph from the bottom up and to the right, or from the top down and to the right. Those are a representation of what's called the ITIC Sabima curve, which is a standard in North America for all electronics design as a impact voltage. So we expect voltage to be in the zone between those 2 lines, and when we design that piece of electronics, that's what we designed it to. That's the spec. Even though when you pull up a data sheet on a product, it's typically going to say voltage plus or minus 10%. That's an accurate statement out here. But if you really have an event that lasts 1/10 of a second, the components inside of that thing are designed to deal with a drop to, about 70% or up as high as 120. So almost plus or minus 25% on those short-term events. More rugged. However, it also says something else. If we have events that are below that line or above it, we're now not just past the spec on the product. We're past the design parameters of the individual components built into the product. What's going to happen? Well, I don't know, but it won't be good. Right? It's going to be bad. And the further off we are, the worse it's going to be. Right? So as you look at this graph, you start to immediately go, how big is my problem? Right? Now this one isn't so bad. They only have a few events that are below that line. But let me tell you this. If this was a report that came from a hospital, this would be bad. Because in the hospital, they draw a line right at 80%. They know that even though their MRI machine is going to take that picture, that CT is going to take that picture, if they have an event that happens when that machine takes that picture that's below 80%, the data is not going to be any good. The picture is going to be corrupted. They can't trust it, right? So in some businesses, even though you run, it might not be good news. And so you have to set some limits. And they've learned that over time. That's just one of the reasons they monitor it so closely. The other thing that is on this graph is a concept of time. So as we move across from left to right, we see events that last longer and longer and longer. In the shaded area, in the green shaded area, that's 5 seconds, right? That's a log graph, so it moves differently, but that's 5 seconds. And if you move way over to the right, you're talking about long-term outages. And as we look at the data and how it falls on our graph, we can start to understand what types of technology are needed to solve the problem. If all your problems are down here in the under 5 second area, you've got 3 different technologies you could pick from to solve the problem. If all your problems are way up here in the outage area, you only got one. Well, it's kind of a combination. You either got a UPS to a generator or you have a flywheel to a generator. That's it, if you're going to really solve those problems. Otherwise, you're going down, right? And so everybody, as they look at the data from their own locations, and they can start to understand what's happening and how painful it is, they can start to make that return on investment decision. Am I satisfied solving 98% of the problems down here, or do I really have to solve those other 2% that are way over here to the right? Because this one's cost X, and this one's going to cost 10X, right? So it gets pretty simple to start to do the math. How much is it worth to solve those 2 more problems? At the back of all these reports that I'm passing around, there's a complete list of all the events that were captured. It's time and date stamped. It tells how low did it go and how long did it last, so 67%, 80 milliseconds, and was it outside that ITIC curve? So it gives you a way to go back. Now, why is that important? Well, I don't have a monitor at every one of your locations, right? But we have a lot of monitors out there, and there's some nearby. Nearby here, this is Kenner, I believe, right? So it's not too far from here where we are here in New Orleans. There's some other ones. Lake Charles is one of the reports that I'll show you here. Point is, if you have a business in that area or nearby that area, you may be able to use data that came off the grid from that area that shows, and you look it up and you go, oh, my records show that this would be 7:40 p.m. I had downtime. Well, gee, at 7:40 p.m. you had a pretty good voltage sag that hit. Not a terrible surprise. So you may be able to use data from an area to give you some sense of what's happening in your own facility. It's always a case where you're going to have to probably have your own data to write that ROI. This is actually that event on Sunday, May 8th, dropped to 67%. When I look at it this way, and again in the report, you could print every one of these events out, see the waveform, RMS values, and data. If you get an email, this is the email you get. It looks like this page. If you get a text message, you're going to see what's at the top. It happened on Sunday. It lasted 4.8 cycles, and the phase dropped to 67%. The other thing it shows me when I look at that is I was only monitoring one phase. So this report that we've been looking at here is really only a third of the events. Because the reality is, right, you got 3 phases of power. 60% of the events out there that happen on our grid are one-phase events. But which phase? I'm only monitoring one. Now, the customer that's doing this has been doing it a long time and is apparently happy with that. This is a different report from Lake Charles. Here you can see a whole different game. Lots more of events that have occurred. Now, this is actually 2 years of data. So in 2 years of time, they had 152 events. Divide by 2, and you go, okay, my average year is going to be 71 events, or 76 events in this case, right? Out of those, 56 were below the Sabima curve. So again, in an average year, you're going to have what, 28 events drop below the Sabima curve at a site if you're out here in Lake Charles. Right? That's your average. That's what you can expect. And here's 2 years of data. We've now got 15 years of data stored in our computers, and what I can tell you from that is every year is the same as last year. It's just a different day and a different squirrel, right? But it's going to happen. You're going to have storms. You're going to have animal interaction. You're going to have somebody hit a pole. We just don't know when they're going to do it. So it'll look very similar. Here we can see a lot more events drop below the Sabima curve. And this is a representation of all those events over time. So the other thing we can see here is, again, we're in Louisiana. Things are pretty constant in terms of temperature and environment here. If you saw this graph for Michigan, for instance, where I'm from, you'd see a bell curve where a lot of those events are in the spring and summer, and not too many of them happen in the winter, right? So as you walk around the country, you see little differences that way. Same kind of thing, we can now see what event took place, how low did it go, and then this is a 3-cycle graph. This is what would have gone to the owner of that monitor within a minute of the event. And you can see by looking at this, you can look at the numbers, okay, went to 41%, but it becomes pretty obvious this is primarily a single-phase event. And anything on that phase went down, and of course 3-phase equipment also went down because one of the phases got creamed. The other 2 single phases aren't too low, probably rode through. So some controls rode through, and some 3-phase, or most 3-phase stuff went, and a lot of other controls went down, right? That's what would have happened in the factory from this kind of event. Would you have figured it out? Well, I don't know. It's not terribly long, 56 milliseconds. Maybe the lights flashed, maybe they didn't. And this, I just threw this in here from Clearwater to let you feel like you're not alone out there. So they didn't do too bad. This is a single year, 86 events. That's pretty normal. Down in that part of the country, lightning capital of the world, it's not unusual to see 100 to 150 events in a year. So again, very similar. So we're finally kind of down to the point of you talk about, well, what do I do about it? Well, for most people, the first thing to do is call their power company, right? This is what you do about it. Fix it, fix it, fix it. Well, here's the reality, guys. The power companies are on the hook for reliability of power. That's their job. Their job is to give us reliable power. Sometimes to increase that reliability and to deal with the grid the way it's designed, they get that reliability by switching around the problems. You hit a pole, it would have knocked the power out to that plant. They don't want that plant to lose power. They switch the power around that problem. The switching action itself, the transfer switch, transmits a 50 millisecond voltage sag down the line. So sometimes that switching action is actually creating some power quality events. And then let's be real. They can't stop the lightning. They're not going to stop the squirrels. They can trim the trees, and that helps. But reality is there's limits to what they can do. And therefore, in every power company in the whole of America, right, there's some words like these, right, that say, hey, if power quality is a problem for you, then you got to fix it yourself. You can't expect the power company to fix that. Now, they'll do the best they can. You're their best customer. They want to do the best they can. But there's a limit to what they can do, and if you push them hard enough, you know, there's some fine print out there that says it's not their problem. So if you're having a problem with unscheduled downtime, step up to the plate and do something about it. You can't go back and lean on these guys. Not gonna help. In fact, I mean, this is data taken from one of these reports. This is often what I find. So here we're looking at regulation and imbalance on the line. This Isense monitor every day is reporting. They put it in 10-minute buckets on just what kind of job the power company's doing. And that picture says they're doing a really fine job, right? And it is what I see most of the time. These things are well regulated, they're well balanced, except for that moment in time that squirrel got there or that lightning hit. It's great, right? And that's what we see across the country today. The reliability has gone up. 90 used to be, when we started in the mid-90s, 96% of all events were under 2 seconds. Today it's 98%, right? The outages have gone down. We don't see brownouts very much more anymore. It's really, really changed in a very positive way, but we're still suffering with power quality. So the second step, having a monitor, reporting that data to your skilled tradespeople, the people on the line closest to it, is going to let you do this pretty effectively. It's going to let you say, hey, when that process went down, it was down for 15 minutes, and I had a report that it was power quality problem. So now you know where it came from. When the robot needed to be rehomed, I know it was a power quality problem that caused it. I don't have to go back to the robot manufacturer and say, hey, it's broken, right? So you got a way to start to put that smoking gun together, and then you can finally do something about it. Now, what are you going to do about it? Well, there's 3 technologies that exist that can solve this problem all the way to 0 volts. The first one of those we know very well is a UPS. Now, I'm not talking about the cheap offline standbys, etc., but an online UPS. I run off the batteries. I trickle charge the batteries with the power coming in off the grid, and I run my operation off the battery bank. If I do that, as long as the batteries are good, I don't care if the squirrel died. It's going to be just fine, right? This, typically, you know, you get enough batteries, let's say you could have 15 minutes of energy. Now, you can imagine if you got a 1200 amp, you know, load, you got a big battery bank. It's filling up part of this room in order to have that much energy. But it happens all the time. We see it everywhere. Second choice would be a flywheel. Now I'm actually going to generate my own power. I'm going to use the power from the grid to spin a 2,000-pound weight. I'm going to spin it at a couple thousand RPMs so that when the power is interrupted on the grid side, that weight keeps spinning. It's like a top. And I can tap off the back side of that for power for about 15 seconds of usable energy. Right? And then it's going to slow down too much. But it's going to give me some amount of time if I use a flywheel. The third choice is what we call a DISC. It stands for Dynamic Sag Corrector. That device, and I'm going to explain how it works, is a little different than the other two. That device is going to be able to correct these problems for 5 seconds. So as you look across, all of these have the ability to protect to 0 volts. UPS maybe 15 minutes, flywheel 15 seconds, DISC 5 seconds. Where does that put you? Looking at the data, right? How do you know what to do if you don't have the data? If you have the data, now you can say, hey, I can use any of these 3, or hey, my only choice, you know, is going to be a ride through the generator. I have a big UPS or something, right? So you need to know what's going on. Now, if you can use a DISC, it's going to cost you a whole lot less money, right? So again, why use the data? Because all of these have different price points, right? A DISC, it's a series device. The power flows from the utility to the load through a static switch in the DISC. So it's in series with the load. And it's monitoring all the time, monitors that waveform. When it sees that voltage drop or the 0 crossing point of the waveform shift, then it turns on and becomes a power supply. And when it does that, the power now flows from the utility down through something we call a power matrix, then a double conversion power core, goes AC to DC and back to AC, and I actually rebuild the sine wave, true sine wave, just like it looked before the event started to happen, and that's what comes out and powers my load. Now the thing that makes this all work is it accomplishes this in less than 2 milliseconds from the start of the event. Okay? So it's fast enough to get ahead of any reaction. It's 3 times faster than anything else. The IP in this device, in this product, is all around this switching. Right? And when I switch, what I'm able to do is pull current from wherever I have it to prop up voltage wherever I need it. So in that same 2 milliseconds, let's say phase 1 drops to 0 volts. I'm going to double the current on phase 2 and prop up the voltage on phase 1 using the energy I just stole from phase 2. So I can steal from Peter to pay Paul. The limit is I can only do this for 5 seconds because I'm doubling current, and if I went longer than that, I would violate the IEEE standards on the wires and the breakers that are feeding the system. Right? So to stay within the IEEE standards, the 5 seconds is a limit. So all the discs that we have, little ones to great big ones, all work exactly the same way, all have the same capabilities and limitations. They can deal with this problem for up to 5 seconds. This is what it looks like. So this is an actual event that's been captured using a 6-channel Isense monitor. So we had 3 channels looking at the power coming in. We have 3 channels looking at the power going out of that disc and a single trigger. So when the event took place, this is what it looked like. And we captured the 3 cycles before the event started, then the event itself until it finally ended. This is the output of the disc from the start to the end. And you can see the waveform, the sine wave has been reestablished through that. And when we look at the RMS values over here on the right, what we see is this was catastrophic in the first 50 milliseconds. All 3 phases dropped almost to about 10% remaining, not quite 0. Then they came up, except they didn't quite make it. And then it kind of dinked around for almost a second before it finally got up over 90%. So the disc turned on here, when the output RMS values. You can see it turned this horrible thing into a little blip, and then it stayed on until finally this had recovered up over 90%, and then it handed back to the line, and it waited for the next event to happen. So if you think about this for a minute, the Isense reports that I've showed you and passed around in those list of events, if you added up all the length of time of all those events on those reports, maybe it equals 5 seconds. Maybe on that 2-year one, there's 10 seconds. That means that the disk is going to run for 5 seconds a year, right? Or in the case of 2 years, maybe it's running 10 seconds a year. Now, if I solve this problem with a disk, the disk is running 5 seconds a year. If I solve this problem with a UPS, the UPS is being trickle charged 24 hours a day, 7 days a week, and it's giving you 5 seconds of protection. It's a 92% efficient device versus a 99.5% efficient device, and that makes a huge difference. At 9 cents a kilowatt hour, here's a rule of thumb, 9 cents a kilowatt hour, if that's what you pay for electricity, 100 amps of UPS, three-phase UPS protection is going to cost you $10,000 a year to trickle charge the batteries. You're going to spend $600 in that same year on a disk. Right? Even that little UPS you might be using in your control cabinet today, on average, $350 a year trickle charging the batteries in that little bin, the guy in the bottom of the cabinet. Right? Just due to the efficiency. That's the nature of the beast. And, of course, that is going to fail sometime about 3 years out. One of the cells is going to go bad, and you're going to have to replace the batteries. Throw away the UPS if it's a little one, or replace the batteries if it's a big one. Right? If it's a big one, you'll have a maintenance contract going along with it. Right? With the disk, its design life is 15 years. It'll be in spec for 15 years. No replacing batteries. In the mini disc, there's no maintenance whatsoever. And the bigger ones, all you got to do is keep a filter clean. And the end result is that the savings in just electricity alone is kind of staggering. And I'll show you some numbers on that. But before I do it, I want to show you a little demo, and I'm sorry about that ugly picture up there. So I've got a demo here of a disk and also a typical load, and it's got a sag generator as a part of this. So we're actually going to create some voltage sags. We're going to put a camera up on screen and look at, not me, but our device. Okay, so we'll catch the rest of the world up with us, and let me explain it a little bit, and I'll put my hand in here and point to things. So what we have over here is pretty special. This is the sag generator. Right now, coming in on the line, I'm reading 121.4 volts. Right, so I'm plugged into the wall right over there, and that's the power coming in. I can use this and change that voltage, and here I've dropped it to, say, 69 volts, and then I can determine for what length of time I want that event to occur. So it'll sag that voltage as if a squirrel hit the line or something happened, and then it'll come bouncing right back. Now, on this side, what we have is typical controls that we might see in any of our control cabinets in the manufacturing floor. I've got a little program running in my PLC at the moment. If anything drops off on this side of the screen, I'm going to turn on a red light indicating where these things begin to fail. Okay, so I can see the effect of it. And to begin with, I'm going to start this without any protection. So this is a normal unprotected circuit reacting the same way it would today in your plant environment. And rather than just pick anything, I'm going to go to my power quality report. So let's reduplicate some real events that happen. So we'll start with this one. This is off the Lake Charles report. And on a November 2nd, this is a 2-year report, so this says 2015, it dropped to 70% remaining voltage and lasted 40 milliseconds. So I'm going to set that up on my machine here. I'm going to go to 40 milliseconds, and I'm going to go to 70% remaining. Just about. Okay, and then I'm going to create this event, and we'll see any effect it has over there. And if somebody's really fast, they can see that thing count for 40 milliseconds, but you'll have to trust me, it does that. So I'm going to create that sag, and I'm going to see over here on the load side and I don't know if it shows up on the camera, I think it does. We can see that we just dropped that relay offline, right? So this little sag, it's a short event. I mean, let's say that's just over 3 cycles. What if it was just over 1 cycle? I'm going to reset it. Let's reset. I'm going to create the same event again. And we see the same fault. So even though this thing is down to just barely a cycle in duration, and it's a very mild sag, this relay dropped offline. Now the PLC is running, so in your manufacturing environment, what would happen? Imagine this was your controls and your compressor. What's going to happen? The controls are going to shut the compressor down because this wasn't supposed to happen. That relay shouldn't have popped. Maybe that relay is a safety gate. You know, somebody walked through it. For goodness sakes, the PLC is going to take action, it's going to shut you down. Then you're going to come up and investigate it, and you're going to look in your PLC, and you're going to say what? Charlie, why'd you walk through the gate? Because you're not going to think it had anything to do with power. The lights didn't blink, it's only 2 cycles long. It couldn't have been power, it had to be Charlie. Or it's a broken machine, so we better go fix it, right? This is what's happening all the time out there. All right, so now, it's interesting, I got a couple of relays in this demo, but only one of them dropped. Right? So I'm going to show you something here. I'm going to take a couple more volts out of that. So I changed this, reset that. So I changed this down from about 82 or 83 volts, about 70% remaining, down to about 67% or 68% remaining. We'll create the same event. Guess what? I just lost both relays. Right? And this will happen over and over. It's totally, it doesn't, I'm not looking at one's better than another. That's not the case here, guys. It's just an example that in all the electronics we have out there in our manufacturing, we design and build that piece of gear the same way every time. That relay is going to act the same way every time. But also, let's be fair, there's a lot of people building that gear. There's a lot of pieces of equipment to choose from. And in our cribs, these are totally interchangeable parts. You got a relay that's down, grab one and go put it in. So remember our guy who's going out there looking at 2 machines, machine A and machine B? And machine A is down, but machine B isn't, and he's scratching his head going, why? They're exactly the same. I bought these 2 machines the same. Yeah, but you bought them 2 years ago. How do you know somebody didn't service something in there and exchange a part? Maybe a relay, maybe something else. They're not the same anymore. They're a little dinky bit different. And as a result, the squirrel that died 2 miles away had a different effect on you than the one that died 1 mile away, right? Now both machines just went down instead of one machine going down. How are you going to figure this out if you're not monitoring? You really aren't, right? You're going to do the wrong thing. You're going to continue to do the wrong thing because you just don't have the data that you need to do it. Let's just create a couple more here. Let's do some, here's one that dropped to 49% for 70 milliseconds on April 19th. So let's do that. 49%. Okay. And reset, we're good. So I'm gonna, okay. So now I lost both those relays and a counter. So, you know, encoder. Think of an encoder. There's a lot of lines out there. It's got an encoder on it. Which bottle's going to get knocked off? Which tire's going off? Oops, the encoder just went down. Control's probably going to stop the whole line until you figure out why the encoder went down. Somebody's going to troubleshoot that encoder and drive themselves nuts trying to find the problem. Again, it's 70 milliseconds. You know, would the lights even have blinked? Probably not. All right, I'm going to do one more and we'll call it good. Here's the one that happened on December 7th and went to 38% and lasted more than a second. So I'm going to go down to 38%. And I'm going to go up to a second. What was it, a second and 2? 1 second and 20 milliseconds. Got to get that in there. All right. So I'm going to, I should have reset that. Okay, we'll create that sag. All right. Okay, that probably did surprise nobody. Yeah, you get bad enough, they all go down. PLC will run out, everything will just fail. All right. So I'm gonna leave it set there, kind of our worst case, it also happens to be more than a second, so we can see the numbers count. So I'll ask you to notice the timer up here, and all I'm going to do is I'm going to reset this, and now I'm going to put in series with this load the disk. So now I'm going to put protection in front of it using this dynamic sag corrector. I'm going to create the same event we just did that lasted just over a second that affected this line. I'll warn you, it might be kind of boring, except for those numbers changing, but let's start that sag. Kind of boring. Everything just goes, right? It just works. So the disk turned on. I guess I didn't need to reset it. There's nothing to reset. The disk turned on, and I'll do it again here. You can watch those numbers count. Okay. Recreated the sine wave, just like it used to look. The equipment doesn't see any problems whatsoever. Right? Just works. And then it hands it back to the line and waits for the next event to happen. Right? Simple as that. Let's go back to the slides for just a couple more. I'm pretty close to my 1 hour, guys, so I'm trying my best here. We'll be back on us. Oh, goodness, get me off of there. There is a video of me doing this, so, you know, for those that really can't get enough of me. This is just a snapshot of these discs. I want to use it to, so we've been looking, and that's a mini disc. That's a 2-amp disc over there. We make single-phase product up to 50 amps. When it gets past 6 amps, instead of looking like a VME, a DIN rail mounted board, it now looks like a small panel, and it hangs on the door or hangs on the back of the panel, again up to 50 amps. On the 3-phase world, we call it Pro Disc or Mega Disc. We kind of divided the line. The Pro Disc describes products that go from 25 amps to 200 amps, okay? So here we're looking at a 50 amp product. It's got an interface on it. You can go back and call back the events. You can see what happened. And that 50 amp device would be about this wide, this thick, and about this high. Right? As they get bigger, 200 amp looks like a small refrigerator. Right? This is a 400 amp, and at the 400 amp level, we call them mega discs. They go 4, 8, 12, 16 on up. These are bus level solutions. In this solution set, the inverter cabinet is here. The IGBTs are all in here. This cabinet here is switchgear. So at that level, it comes with auto bypass switchgear. It'll actually bypass itself if it had a problem without dropping your load. Right? It's designed, you know, one of our biggest user in the world of this product is the semiconductor industry. And in their world, a downtime event's $1 million. They don't want it to go down. I don't care whose problem it is. If you got a problem, don't take me down. So this gear won't take them down. Right? This cabinet over here contains extra capacitance. So the way the disc works is it steals current to prop up voltage. But if it doesn't have enough to steal from, it adds current from capacitors. So imagine one phase goes 0. I just double the energy out of phase 2 and prop it up. All 3 phases go to 40%. I double the current. That only gets me up to 80%. It's a 1-to-1 relationship. So now I dump energy from capacitors to push me up over 90%. The other thing this does for me is it gives me energy in the case of a true outage. So for most of us, once a year we may have an outage. And when that occurs, we can't steal current from nothing. What we have is our capacitive energy left. And as long as we have at least 1/10 of a second at running load, then we're going to protect your equipment from damage. Because in a real outage, imagine a real outage now. Somebody hit a pole, they're going to take you down, the lines hit the ground, they short, they bounce, they short again. Maybe on the 3rd try something breaks and they cross. Now the phases swap. In that first 1/10 of a second, all this ugly voltage signature comes rushing down the line at your plant. The disc turns on, protects you from all that. Finally, it runs out of energy, hands it back to the line. Well, by this point, the breakers have all popped, the line is dead. So you get a clean drop to 0 instead of some awful drop. So your equipment's protected from damage due to an outage, and it rides you through all the sags. So they all have some capacitive energy. We actually make 3 or 4 different sizes depending on the load. So we would actually look at how much load do you have on that circuit, what kind of experience have you had, what's the data look like, and then decide how much capacitive energy you need to ride through all the stuff. Right? So you have some choices there. Oh, this I promise to, you know, this is one of those slides where people just don't believe it, but it's just real. This is simply math on the difference in the efficiency, 92 to 9.5% between a UPS and a disk. And here we're looking at something for a 1200 amp application. In 5 years' time, that's $450,000 difference in the cost of electricity, right, and trickle charge and batteries. So in some cases, you know, Duke and others will actually give you energy credits for using a disk instead of a UPS, because that's real. That's a big, big difference in how much energy you're going to hog. So on big plants, that can make a difference for you. But it's true at any size. It's that same equation. And finally, I'm to the end of this thing, and I really like to leave it with a little discussion of what the next steps are. And what I think the first thing you need to do is, within your own facilities, is you need to discuss in a group, you know, what's the priorities? Where is the pain? Now, it's bad when everything goes down, but let's be real. Some things you really can start every time by pushing a button. That's a lot less painful than the extruder or the blow molder that went down, which is going to spend hours cutting stuff out. So get simple. Start making that list. Here's the priorities of what I want protected, because it's really painful when it goes down. Right? Don't just say, oh, protect the whole plant. Most people can't afford that. Let's get real. What's painful? Right? And then go to your single line drawing. And with that drawing in front of you, circle the feed to all those pain points you already decided are important. Because now you can look at a diagram and say, you know what? There's 4 of these guys right here that have to be protected, and they're all fed out of this same bus. So I could put one, maybe it's a 400 amp unit up here, instead of putting 4 100 amp units down there. It's going to cost you less money per amp to protect it that way. You're only going to do 1 install instead of 4, right? And all the rest of the equipment that's on that bus is protected anyway. So your power supplies will last longer, and your drives will last longer, and you get a lot of secondary benefits. But it starts out by protecting the pain points. You know, correlate your downtime. You're going to have an ROI. You got to have some data, and you got to have the smoking gun. What's it really costing me? Make sure you have that data. And then finally, if you're down to the point where I want to do something, measure the actual running loads. Because one of the things we're famous for in industry, right, is we oversize. So we're going to put a 400 amp breaker on this side, and we're going to feed that circuit, and boy, we're going to be good, because when you actually measure that circuit, it's drawing 57 amps. You go, okay. And the way the disk is designed is I can pull startup current through it. I can pull 150% of its rating for 30 seconds. I can pull 600% of its rating for half a second, a linear equation between. So what that means is startup currents, I don't have to oversize the disk to deal with startup currents. I size it to the running load. So clamp a meter on, measure your running load. Don't just go by what size that breaker is. All right? And now we're going to be able to get the cost of that solution down as low as possible by actually measuring those loads. And then build the ROI, and ask for help. If we can help you, we certainly will. If you need references, we certainly have them. You know, we're out there today in all these industries in a very big way, and from little bitty pieces to great big pieces, and everything in between. And people are willing to talk about it. I mean, Intel talks to Samsung about this problem, right? It's the same problem for everybody. So it's usually not a big secret. You know, it's not hard to get a reference. It's not hard to have somebody tell you what they've done and what they've done to correct the problem. So with that, I'm going to open it up for questions. If you had any questions from anybody here, speak up, and anybody online, you can pass them along for me.
Yeah, online audience, feel free to type in a question. All of our phones are muted, and we don't have our speakers on today anyway, so we won't be able to hear you talk. We have a question in the room.
Go ahead.
Does the disk provide any kind of protection for overvoltage transients?
Yes, thank you for asking that. It's a very good question. I always spend all my time talking about voltage sags because it's the big issue, but spikes can happen. right? Reality they can. So there'll be more questions. So the bottom line is yes. So all of our big stuff has like a MOV front end on the disc. So if you get hit by a spike, it's going to protect you and protect downstream, protect the disc and protect what's downstream. And there'll be replaceable parts. Now the mini disc has protection in it, but if you hit that enough times, you're just going to fry the mini disc. You're replacing it. So if that's a risk on the single phase side, you should be putting some protection upstream. It's cheaper than having to replace a mini disc when it goes. But they all will provide that protection. The reason I don't talk about it much is that on the grid, we take those spikes to ground. So unless you get hit by lightning, like at your plant right where you're standing, if it hits down the street, it's taken to ground and turned into a short to get rid of all that energy, right? So we don't see it very often, at most of it. We don't see it very often as a result.
Okay. And what about harmonics? Does it do any?
So the disc does not do anything for your harmonics. If that's a problem, there is a different solution, and Rockwell offers solutions to harmonic issues. It's a different kind of problem. Think of the disc this way. It's going to reproduce exactly what that sine wave was that had been going through and you've been running your plant on. If you had a easy way to think about it, you got a 480 line that for whatever reason, the loads on the lines, whatever, it's at 460. And that's what your plant's running on today is 460, not 480. When a sag comes along and that disc turns on, the output of the disc won't jump back to 480. It's going to be at 460. It's going to look just like it. If you've got problems with your phase balance and that's the way you're running, that's going to look just like that coming out. It'll duplicate anything that's in there. It's going to absolutely going to create exactly that waveform that it had been watching. That's what it's doing. So if you do have those problems, and sometimes you do, you know, we need to go address those because but it's a different solution entirely. Any other questions? Those are great ones. Anything on the line? So I have a question. How many you want? so really, please talk to us about your needs. We'll be glad to take and help all we can. If you have power quality data, because you've got your own monitoring, you know, it doesn't have to come from my Isense monitor or my Power Monitor 5000. It can come from your monitor as long as it's power quality monitoring data. That data is going to tell us the story. So make sure you're doing event capture, power quality, voltage monitoring. That's what's incredibly important here. Good.
All right, Brian. Appreciate the very informative presentation. Thank you. Web
Right,
audience. Oh, applause! Wow, that's a first.
Thank you very
I think it's the first time ever. We appreciate our web audience being on as always and listening in out there and joining us virtually. And we didn't go too bad. It's only 1:09, so I applaud you for that, Brian. Not the 3-hour marathon like we did last year. So with that, we'll wrap it up, and everybody have a great day. And thanks for attending.